Ni hao. Hello. This is the 27th lesson in heat transfer. We have been discussing thermal radiation heat transfer in this unit. And in lesson 27, we will begin to discuss thermal radiation emission from real surfaces. In this first part of the lesson, however, we will first review the most important ideas from the previous two lessons. These ideas are fundamental to understanding emission from real surfaces, and we will need them to form the basis of how we handle real surface emission, which will ultimately allow us to analyze problems like the concentrated solar power receiver that was introduced in lesson 26. There are no new objectives in this part of the lesson. We will review the most important ideas covered so far in thermal radiation heat transfer. On with the review.
A little review here at the beginning, so you should see this stuff in your notes. So don't try to write any of this stuff down. Just look to see that you have some of these ideas already sitting in your notes. This is like kind of a summary of the major ideas so far in the radiation unit. So one, what is thermal radiation, right? It's different than radiation coming from other sources, particularly radiation that is emitted due to some external excitation, right? So thermal radiation is not microwaves. Microwaves are emitted because you excite an emitter unit in a particular way. Thermal radiation is emitted just because matter has temperature. It happens passively. We don't have to do anything special to get the radiation to come out. Any matter that has temperature is emitting this radiation on its own. And it happens primarily, one of the important ways is because of the way that electrons are bouncing around their energy levels. So I like to think of it as playing popcorn with the electrons, right? Which is happening naturally because matter at the microscopic level is bouncing around, and so the electrons are bouncing around. And when they pop high and fall back, when they fall back, they emit a photon, right? And they can get popped high because they're absorbing photons. So that's thermal radiation. There are really four critical processes for the radiation that we will cover in this class, because we're dealing with surface-to-surface radiation. So we're going to exclude radiation that interacts with gaseous volumes or just volumes in general. So for example, if you think about radiation penetrating through a cloud, we're not going to deal with that. Okay, so an interesting, really interesting problem, but one that we won't deal with. Only surface to surface. So we're assuming that all of the space between the surfaces is occupied either by a vacuum or by air that doesn't participate with the radiation. The four processes are emission, absorption, reflection, and transmission. And you should be able to describe those in your own words. You can put them in your glossary if you want. But I like the little sketch to remind myself of what these are too. Right? So emission is the energy, the radiated energy coming out because the surface has a temperature. And then absorption, reflection, and transmission are what can happen to radiation coming into the surface. So radiation can be absorbed, it can be reflected, or it can be transmitted, right? The incident radiation. Transmission means it goes through, reflection means it gets turned around, and absorption means it actually terminates and it gets stuck into the surface. Thanks, Brad. Yep. Yeah.
Would the transmission radiation be kind of like how you described the Q-gen on the first test? And you said it was like had radiation going through the wall.
Good memory. Yeah. Yeah, that was the radiative decay, right? It was coming through. Yeah, so the fact that it could move through that first interface means that interface was transparent to that radiation. Yes. Yep. Typically, we think about transmission as, at least in the context of surface to surface, as it's through an interface. Right? So does it pass through the interface or not? Correct. There's also transmission through clouds where it's a little bit different meaning. Black body surface, the next big thing. The black body surface and the concept of the black body is really fundamental to thermal radiation, radiation in general, I would say too. because this is this like ideal construct against which we compare every real surface. So by definition, a black body surface emits the most radiation possible at any temperature. It absorbs all incoming radiation, and it emits equally in all directions, right? Which means it's a diffuse emitter. Diffuse is always going to mean, in the context of radiation, equal in all directions, right? No special directional dependence. There are two really important equations that you've seen so far related to the black body surface. One is the Planck distribution, that really big, long, nasty one, but I don't want you to recognize, like, I actually don't even want you to think about the equation. When I say the word Planck distribution, I want you to have a picture of the curve in your head. So you remember those curves? They're kind of, you know, upside down parabolas, but they're not just parabolas, they're skewed to lower wavelengths. And that's what you should be thinking with Planck's distribution. And when we integrate over all wavelengths, the Planck distribution, we get the Stefan-Boltzmann law, which is this n squared sigma ts to the fourth. Both really, really important equations for radiation. And then we've started to talk about the equation that you've already seen in the class, because I gave this to you way back at the beginning of the class to handle radiation and problems, mostly because that's where your book did it. And this, of course, this is how a lot of radiation problems are handled. So the net radiative flux, which is always given by the emitted minus the absorbed radiation, is this epsilon sigma surface temperature to the fourth minus T surroundings to the fourth. And we're starting to unpack this and understand where it comes from. And on Friday, we looked in particular at what it means to have a large isothermal enclosure. And I tried to convince you that what's important about the large isothermal enclosure is that it allows us to say something about the incident radiation on the surface. When we are in a large isothermal enclosure, inside of the enclosure, the radiation streaming around is black body radiation, right? With a spectral distribution given by that of the temperatures of the walls. It doesn't matter whether the walls are black surfaces or not. If you are in a large isothermal enclosure, the radiation streaming around inside is black body radiation at the wall, at the temperature of the walls. Like it was emitted from a source with the temperature of the walls. That's really, really important. And that is what, that simplification, allowing us to substitute something for G, is really a big deal, okay? Incident radiation is really complicated. When we start to relax the large isothermal enclosure assumption, you're gonna see how complicated it quickly gets, trying to account for incident radiation from all other possible sources of emission. Things are really, really coupled together. So this is a really, it's a huge simplification, and really one that makes it much, much easier. The other really critical assumption for this equation is that the surface is diffuse and gray. And that means we have to say something about how the emissivity and the absorptivity are related, specifically that they're equal to each other. And we're going to unpack what that means today. Okay, so that's one we're going to dive into today.